We're going to talk about some absolute extrema of a function y equals x squared and look at different domains. So we'll talk about, this is exploring extrema, and we'll talk about absolute right now. Then we'll talk about local or relative maxes and mins. So the absolute extrema of y is equal to x squared changes depending on the domain. Specified. All right, first of all, let's just take a look at y equals x squared and have the domain be all real numbers. So if you want to take a look at the graph, you remember what y equals x squared looks like. And let's say for the first domain, we'll have d means domain. So I'll say d is equal to negative infinity to positive infinity. That means all real numbers. So if the domain is all real numbers, then when you take a look at this graph of y equals x squared, you can see that there's no absolute maximum because it goes up forever in both directions. But there is an absolute min because it comes down and takes on a lowest value down here. So the absolute minimum in this particular domain is at x equals 0. The y value is 0. So let's take a look at different domain now. Let's take the domain restricted down to x is equal to 0 all the way up to 2. 0 and 2 are both included in this domain. So if you took a look at that, just that portion of the graph, I'll just sketch that here. It starts here and it ends here, and it's just a little part of this parabola like that. So there's the domain. Now this one does have an absolute max and it does have an absolute min. The absolute max is at x equals 2 because it's included in here, and the absolute min is at x is equal to 0. So that's looking at this restricted domain. Let's restrict the domain even further. Let's say the domain does not include 0, but everything up until 0, and it does include 2. So if we were to sketch the little graph of this, it would have an open circle down here at 0, 0. It would look just like this one up here, but it just doesn't include 0. So when you have an open interval like this is called an open interval because x doesn't equal 0. This function does not have an absolute min, but it does have an absolute max. The absolute max is still at x equals 2 because it does include that, but there is no absolute min. And now we'll restrict it down one more permutation of this. Let's call the domain going from 0 to 2 exclusively. It means we're excluding those two values of x. So on that domain, you'll have an open circle at 0, 0 and an open circle at 2, 4. So the graph looks like it did before, but we just have open circles at the ends. So in this case, there are no absolute maxes or mins, so there is no extrema on this restricted domain. There aren't any local maxes or mins either. Okay, so that leads us up to something called the extreme value theorem. The extreme value theorem says that if a function is continuous, which means it doesn't have any breaks in it, if it's continuous and it's continuous on a closed interval, like option B up here, then this function has both a maximum and a minimum value in that interval. And that's all it says. So if your function, we'll call it f, is continuous on a closed interval. That means we got square brackets on here. We'll call it A to B. Then F has both a maximum value and a minimum value on that interval. And those maxes and mins are absolute maxes, or an absolute max and an absolute min. All right, let's take a look at some other graphs here. Let's take a look at a graph that might be a cubic graph here. Let's say we have a closed interval from here to here, from A to B. All right, because we have this closed interval, we have an absolute max and an absolute min, and they occur at the interior points. So right here, here's the absolute max. This is kind of a repeat from the other one, but this is really pretty important. This is the absolute max of the function because it's the highest value, and this is the absolute min because it's the lowest point on it, and they occur at interior points, interior to the closed interval. So these extremas occur at interior points on the interval. Interval. All right, sometimes you'll have a graph that looks like this, or maybe it'll go up. But these maximum and minimum points, these extremas, they occur at the endpoints. And like today in class, we were looking at some extreme values, and these have to do with derivatives. So if you calculated the derivative of this particular function, the derivative would be equal to 0 here and here, which would mean these two are critical values of the function, these two x values. These two x values are the endpoints of the interval, but these are the critical values. So these absolute maxes and mins occur at critical values. These absolute maxes and mins, you can see that the derivative will never be equal to 0 or undefined on this particular function. So in this case, the derivative will never be equal to 0, but we still have an absolute max and absolute min at the end point. Sometimes we'll have a function that looks like maybe a quadratic looking like this. It'll come up and around, and then it'll stop right there. So in this particular case, we have an absolute min occurring at an endpoint, but we have an absolute max occurring at an interior point. So the min is at an endpoint. The max is at an interior point of the interval from A to B, if you call it A to B. And then, just for completeness, you can imagine that you might have a maximum at an endpoint and a minimum at an interior point. So right down here, this minimum would occur at an interior point. And the maximum occurs at the end point. So we always have to check the endpoints if we're checking for local maxes and mins. The first job that we have is to set the derivative equal to 0 and solve it for x, because those are the potential maxes and mins. Like right here, the derivative would be 0, and right here it would be equal to 0. But that's not it. We also have to plug in the a and the b value into the original function, because we often don't have a graph to look at, so we don't know what's going to be maximums and what's going to be a max or what's going to be a min. All right, here's, I'm not sure if I mentioned this vocabulary before, but this is just some vocab. And all of the other ones I've talked about are absolutes, but let's talk about local or relative. Relative. extrema is the same thing as local extrema. And when you talk about the relative extrema, you're talking about all the points nearby. So sometimes absolute extremas are also relative extremas. Let's take a look at a similar graph to what we did the other day. If you have a function that looks like this, comes down, comes way up, and then ends here, and this is a closed interval. We have right here at the end point, we have an absolute min, and because it's also the minimum of all the local points or the nearby points, this endpoint is also a local min or a relative min. This point right here, this is a relative or a local max, but it's not the absolute max because it's not the highest value of f of x. So right here is a local min. Up here, this is a local max and an absolute max. And over here, this is a local min only. It's not the lowest, but it's the lowest of surrounding points. So this is the local min. So what we would do if we had a function that looked like this, we just calculate the value of the derivative. It looks like the derivative is either 0 or undefined at 1, 2, 3 spots. So we check the original f of x at those 3 x values, and then we'd have to check them at the endpoints too to see whether or not they're absolute or relative. All right, let's get into an example here. Let's find the extrema of this piecewise function. F of x equals 5 minus 2x squared if x is less than or equal to 1, and f of x equals x plus 2 for x is greater than 1. So let's take a look at what this function might look like on our graphing calculator. So pull out your graphing calculator. Well, make sure the mode is set right. And you really should follow along with your own graphing calculator. Don't just watch me do this one. And if you want to graph 5 minus 2x squared, 5 minus 2x squared, and that is when x is less than or equal to 1, and the other part of it is x plus 2, and that is when x is greater than 1. So this graph looks like it's a continuous graph, but we can confirm that because this looks like it's the breaking point here when x is equal to 1. And to check continuity, because if this was a discontinuous graph, we couldn't apply this extreme value theorem. But let's check continuity. At x equals 1, 5 minus 2x squared is equal to 5 minus 2, which is 3. And x plus 2 is equal to 1 plus 2, which is equal to 3. So because those two values are equal to each other, because 3 equals 3, that means it's continuous. So I'll say, therefore, it's continuous. So that's good. We've got a continuous graph here. And let's just make a little sketch of this on our notebook. So it comes up and around here, and at x equals 1, it starts heading off in this direction. So there's a sketch of the function. And if we want to find the extrema, it looks like because this goes down forever, we've defined our domain to be all real numbers. So there's going to be no absolute min. There's going to be no absolute max. So it looks like we've got a local max here and a local min here. So graphically, we see a local min or a local max at x equals 0 and a local min at x equals 1. But let's take the derivative. So let's find this analytically using calculus. So that's our graphical solution. So analytically, this is using calculus, which means take the derivative. F prime of x, we set that up as a piecewise function, just like the one above. So f prime of x is equal to negative 4x when x is less than or equal to 1, and f prime of x is equal to 1 when x is greater than 1. So if you set the derivative equal to 0, this is the part of the graph. This part is the graph where the derivative is equal to negative 4x. So if you set x equals negative 4x equals 0, you get x is equal to 0. So there's your critical value. I'll label it as a CV, critical value. And if you wanted to do a sign table on that, if you put a negative value in here, it would have a positive derivative. And if you put x is greater than 0 in, it would have a negative derivative. So a graph that goes from a positive derivative to a negative derivative means it's going up and then it comes down again. So if you kind of mentally did a sign chart on that, you would see that that would be a local max because the derivative changes from a positive, it goes to 0 there, and then it goes to a negative value. So that would be our local max. And then here at this breaking point, when x is equal to 1, the derivative is negative 4. So f prime of 1 is equal to negative 4. And if you tried to find the derivative here when x is greater than 1, then that derivative at this breaking point would be equal to 1. So we have a derivative of negative 4 to the left of this critical value, and we have a derivative equal to 1 to the right of the critical value. And because they're not equal to each other, you have a sharp turn. So a sharp turn indicates, indicates an undefined derivative. So at x equals 1, the derivative is undefined. And because it's undefined, you know you're going to have a local max or min. And so you can just plug in x equals 1. And you can see that, or x equals any number between x equals 0 and 1, you would see that you'd get positive or greater than 3, and then any value of x greater than 1, you would also see you'd get y values that are greater than 3. So that means that x equals 1 isn't local min. And let's do one last example. Let's find the extremes of y is equal to x cubed minus 3x squared plus 3x minus 2. And I'm going to have you find this over the domain of not including 0, but going up to 2, including 2. All right, and this is, let's say we don't have a graph of this, so we're not really sure what this is going to look like. So what we need to do first is find y prime. Y prime of x is equal to 3x squared minus 6x plus 3. We're going to set it equal to 0, so we have a 3 as a GCF, x squared minus 2x plus 1. And if we divide both sides by 3, the 3 will cancel out. And so what we have left is x minus 1 squared is equal to 0. So x is equal to 1. So that is the critical value. And now we have to set up a sign table. but 0 is really not included, even though we're going to take a look at x equals 0, x equals 1, and x is equal to 2. And if we plug in x equals 1, we know that we have a 0 derivative. This is a sign table for f prime of x. And our sign table is going to help us find the extremes of this. All right, so what we're going to do now is we're going to plug in our endpoints of 0 and 2, but 0 really doesn't count as far as our local maxes or mins go. So if we plug in x equals 0 to this original function, we get the y value is equal to -2. So 0, comma, -2 would be 1 point on here. If we plugged in x is equal to 1, in here we get 1 minus 3, -2, plus 3 is 1, and 1 minus 2 is -3, so 1 negative, is that right? No, 1 comma -1 would be that value. And if we plugged in x equals 2, we get 8, and then minus 12 plus 6 minus 2, we get 0. So 2 comma 0 would be those 3 points along the line. Well, let's see what happens to f prime of x. This is a sign table, so we just have to indicate a plus or minus in here. So if we plugged in a number like x equals 1/2, so what we need to do is figure out whether the derivative is going to be positive or negative for any x value between 0 and 1, and for any x value between 1 and 2. And so remember, this right here is the sign table for the derivative. What I calculated here were the actual f of x values. So when x equals 0, f of x is equal to this number, -2. But right up here, the sign table for the derivative means that I'm going to go back up to the derivative here, this 3x squared minus 6x plus 3, and I'm going to calculate whether this is positive or negative. So I'm just going to go off to the side. I'm going to choose x equals 1/2. That's probably the easiest number to choose between 0 and 1, and plug it into f prime. So let's figure out what f prime of 1/2 is, so we know to put a plus or minus there. Well, f prime of 1/2 is 3 times 1/2 squared minus 6 times 1/2 plus 3. Well, that is equal to 3/4 minus 3 plus 3. And that would give us a positive 3/4 answer over here. So I'm just going to be putting a plus sign right there because f prime of x is positive there. That just means that the graph is going to go uphill. It's going to have an increasing slope. Now let's figure out what f prime of a number between 1 and 2. I'll just choose 3/2. So let's do f prime of 3 over 2. So that's equal to 3 times 3/2 squared minus 6 times 3/2 plus 3. Well, this is 9/4 times 3 is 27 over 4 minus, this is a 9, and then plus 3. So this is 13.5 minus 9 is 4.5, I guess, plus 3 is 7. This is going to be a positive number too. So our sign table shows that this graph is going to go up, and then it's going to hit x equals 1 and it's going to flatten out, but then it's going to continue to go up again. What we have is no sign change on this sign table. On the f prime of x sign table. Oops, sign table. So what that means is, like I said, this graph is going to, starting at x equals 0, this graph is undefined at x equals 0, but then it's going to go up. It's going to have a derivative of 0 at x equals 1, but then it's going to start heading up again. So we have this critical value here. Here's our x values. X is equal to 0, x equals 1, and x is equal to 2. And the y value here is 0. So this point right here is 2, 0. This point here is 1, negative 1. And this point, if it existed, would be 0, negative 2. So let's talk about the extremas, because that's what, or the extrema, that's what the original question asked. So what about a local or an absolute min? Well, because this never gets down to the lowest point, there's no absolute min and there's no relative min, because you can't ever get to a lowest point on this graph in the interval between 0 and 2, excluding 0, but including 2. But now let's talk about the absolute and relative maximum. Well, right here at this critical value x equals 1, this is neither a local max or a local min, because to the left of it is lower, to the right of it is higher. So this critical value, even though 1 is a critical value, it is not an extrema. X equals 1 is a CV, that means critical value, but not an extrema of any kind. So what happens is this particular graph has an absolute and a local maximum over here at x equals 2, and that's it. So the absolute and local, or the relative max, is at x is equal to 2. And that kind of makes sense too when we looked at the y values. This y value was the lowest, and this y value was in the middle, and this is the highest y value that we calculated from the f of x function. But you can also find it using derivatives. So that's it for today. We'll do more exercises tomorrow. Have a nice night.